The next section we want to cover is about the physics of rotation. And this first video is going to be about the kinematics of rotation. And if you recall kinematics, we talked about that in chapter 2 in relation to regular motion. Kinematics is just describing the motion. It was before we got into the reasons for the motion, so the force, and then of course momentum and energy came afterward. So this first video again is just going to be on how do we describe rotational motion. You want to be thinking about an object moving in the following way now. Two kinds of motion an object can have: translational motion and rotational motion. So up until now, all the motion we've been talking about has been translational. We haven't used that word because we didn't have to distinguish yet, but now we do. Translational motion is just an object moving through space. The object itself is sort of moving from point A to point B. That's translational motion. Rotational motion is sort of internally, right? The object may be spinning, rotating. And of course, in general, an object may be doing both at the same time. It may be moving through space and at the same time rotating. So these are the two kinds of motion. And in general, you sort of have to treat both. Of course, up until now, we've been completely ignoring any rotational motion. Now, some examples that will sort of be what you want to have in your mind as we continue with this video. You might have a rigid object, so just that like an object that can't, its individual parts can't move away from each other. A rigid object that is actually fixed where it is in space, but it is able to rotate around an axis. So think of like a record player, a record on a record player. So it's just a circle, that's a disc that spins around and around. It's not moving anywhere, but it's spinning in place. So that kind of situation would be all rotational motion, no translational motion. And a lot of what we're going to talk about is you want to have that picture in your mind. But I don't want you to ignore that we could also have, as I said earlier, an object that is doing both. It's moving through space and rotating. So maybe you throw a ball in the air. And not only is it moving through projectile motion, but it is also spinning. It is also rotating. So we have both kinds of motion in that case. Anything that's rolling, of course, does that, right? It's moving and it's rotating. So a rolling object is a good example. And then finally, we even have another case that could be included in what we're talking about, where the object may or may not be rotating, but its translational motion actually can be viewed as rotating around something else. So we could think of any kind of circular motion of an object, like the Earth going around the Sun, for example. We've dealt with that before, so that's not new. That's translational motion, and it's just that the motion happens to be in a circular path. But it's actually possible to think of that instead of as translational motion as rotational motion. Think of it as just this one point, this particle that's rotating around the Sun. So these are the different cases that what we're about to talk about could apply to all of these things. So we have to get into how do we describe motion, rotational motion. And the fundamental concept here is that rotational motion pretty much acts like one-dimensional translational motion. We're going to have position, we're going to have velocity, and we're going to have acceleration, our three quantities that describe motion. But we're going to tweak them so that they work for rotating instead of just moving through space. But yeah, it's going to be kind of a 1D problem, because if you're rotating, you can only go in two directions. You can go clockwise or counterclockwise. Just like in regular 1D motion, you either go to the left or to the right. So yeah, that's the analog. The analog here is one-dimensional motion. But we have to talk about the tweaks that we're going to employ. So position now is actually going to be an angle. We're going to measure position as an angle, and I'll describe that in a second. And then from there, it's going to be like before. The derivative of position will be the angular velocity, and then the derivative of that, so the second derivative, will be the angular acceleration. So again, we're going to have these three quantities with these derivative relationships, just like before. Okay, so let's talk about rotational position. Let's say we have an object, and just for simplicity, I'll kind of draw a circle. And we're going to put a coordinate system on it. Now, when an object spins, that's kind of inherently a two-dimensional picture that we draw, right? Okay. Now, what we're going to do is we're going to take one sort of line from the center, and I'm assuming the center is like where this object is fixed. That's the point that it's rotating around. Okay, so the object is kind of rotating around like this, and that center, maybe this is a record that's on a record player, and it's fixed right in the middle, and it's spinning around its middle. Okay, so we're going to take this one line, and that's what we call our reference line. And as the circle rotates, that reference line will go around. So we will describe the rotational position of this circle based on where that reference line is. Okay, so there it is, and maybe a little bit later it's here, and then a little bit later it's here, and then here, and then of course it might come back around and have gone around one full rotation. Okay, so now how do we quantify that? Well, the way we quantify that is with an angle. So typically we use the positive x-axis as our sort of baseline. That's our 0. So theta equals 0. And then you measure the angle from there. So whatever angle it takes to go from 0 to where you are, that's your position. So we use the letter theta for our position, and it's an angle. It's measured in radians. And it's easier if you do things in radians. If you don't do things in radians, then you have lots of 2 pi's floating around in all your formulas. So it's actually just easier if you just work in radians, and that's what everybody does. Okay, so for example, the picture I have here, this object has maybe, that looks like maybe 30 degrees, which is pi over 6. Let me just remind you that if you have degrees, you multiply by pi divided by 180 to turn it into radians. Okay, that's the conversion factor. And if you have radians, you multiply by 180 over pi to turn it back into degrees. Okay. All right. So yeah, this picture that I have here, maybe theta is pi over 6. 90 degrees, so sort of straight up, that would be theta equals pi over 2. Pi over 2 is 90 degrees. If you go all the way around to the opposite side, that's pi. So pi is 180 degrees. Down here would be 1.5 pi, or 3 pi over 2. And then finally, if you come all the way back to the theta equals 0 line, that's theta equals 2 pi, which is 360 degrees. So notice that 0 and 2 pi are actually the same angle. 2 pi just means you went around, but you're in the same position as if you hadn't gone anywhere. So 0 and 2 pi are the same. And in fact, that's true for any theta. You can add 2 pi to it, and it's really the same thing. In fact, you could add 2 pi multiple times. You could add 4 pi, 6 pi, 8 pi, and it's really the same angle. So angles are a little annoying in that way, in that unlike in regular 1D motion where you have an x-axis and different numbers represent different positions, when you're going in around in a circle, obviously it comes back on itself. So every angle has sort of multiple numbers that correspond to really the same angle, the same position. It usually, in practice, doesn't create too much confusion, but it's important to notice that. Okay. So again, just to repeat, we measure the rotational position of an object by the angle of a reference line that we choose. Again, the reference line, you can choose it to be anywhere you want. And by the way, often you can sort of make the reference line be at 0 in terms of how the object starts out, and that will just make things easier if you start things at 0. But it doesn't matter, it's just a choice. You pick a reference line on your object and then you measure the angle from there, and that's how you tell sort of where the object is rotationally, how it is oriented. Okay. Now let's talk about velocity. So velocity is the derivative of what we just talked about, the angular position. So the symbol we use is a lowercase omega. That's the last letter of the Greek alphabet, and it kind of looks like a W, but usually it's kind of written in a kind of a curled way like that. So omega, and it is the derivative of the theta. And again, this is analogous to v is dx dt. It's the same idea. That's the instantaneous angular velocity. We can also do the average from one time to another time, and that's where we use deltas. The change in theta divided by the change in time. Okay. You can see that the units here would be radians per second. Radians per second. Going to be the units for angular velocity. So, just as an example, you might have, something is moving at a rate of 25 radians per second. Something's rotating at a velocity of 25 radians per second. And that tells you how fast it's spinning. Okay. Now, just a little addendum to this. Sometimes angular velocity can be given to you in sort of a disguised way. There's a couple of common things that are done. One thing that's done is, instead of saying how many radians per second, often in the real world, things are measured in revolutions per second. So let's say 50 revolutions per second. So that's different, right? That's a full revolution. How many revolutions you do in 1 second. So like 50 revolutions per second would be something that's spinning pretty fast, right? Going around 50 times every second. So that's called the frequency, and lowercase f is often used for that. So revolutions per second. Now if you want to convert it to the standard angular velocity measured in radians per second, what you would do is you would multiply by 2 pi, because there's 2 pi radians in a revolution, right? 2 pi, an angle of 2 pi to go around once, and then the revolutions would cancel, and 50 times 2 pi, so 100 pi, it's like 314 radians per second. So 50 revolutions per second is the same as 314 radians per second. So frequency, a common way that velocity can be given, but it's not the true velocity. You have to multiply it by 2 pi to get the true velocity. The other thing that can happen is, instead of saying how many revolutions per second, you can say how many seconds per revolution. So let's say we have 2 seconds per revolution. So this is telling you how long it takes for one revolution. So that's actually a time, right? That's how many seconds per revolution. That's the capital T is used for that, and that's called the period. So 2 seconds per revolution. Obviously that would be slow, at least slower than 50 revolutions per second. 2 seconds per revolution. And what you do here is, first you can flip that to get the frequency. So if the period is 2 seconds per revolution, then the frequency is 1 over 2 revolutions per second. So that would be the frequency, 0.5. And then you could multiply that by 2 pi radians per revolution to get the omega in radians per second. And that would be well, pi, right? 1/2 times 2 pi is pi. Pi radians, 3.14 radians per second. All right, so frequency and period, again, two alternate ways to basically give velocity information, but omega, the thing that's measured in radians per second, is the true angular velocity in any formulas that are coming up. Okay, and now acceleration. So with acceleration, we use the Greek letter alpha, the first letter of the Greek alphabet, lowercase alpha, just as a stand-in for A, for acceleration. And this is the derivative of the velocity, which means it's the second derivative of position, just like with regular 1D motion. Okay, that's instantaneous. We can also do average acceleration if things are changing at different rates, if there's not just one acceleration. And that would be the change in angular velocity over the change in time. This is measured in radians per second squared. Radians per second per second. So again, hopefully you're seeing it's very analogous to one-dimensional motion. We don't necessarily have alternate ways of giving acceleration information like we do for velocity. So that's really all we have to say about angular acceleration. Yeah, it's the second derivative of position. It's the first derivative of velocity. So again, this analogy is going to be ongoing between old 1D translational motion back in Chapter 2 and now simple rotation. So position, now we're talking about angle. Velocity, angular velocity. Acceleration, angular acceleration. And I'll uncover the rest of this list, and the rest of this list are things that we're going to get to as we proceed in this chapter. But you'll see that there's this analogy that goes on and on. So in place of mass, we're going to have moment of inertia. That all has to be explained. In place of force, we're going to have torque. Kinetic energy, actually, we won't have a replacement. Kinetic energy will still be kinetic energy. We'll talk about what kinetic energy looks like in rotation, but that's not even an analogy. That's literally the same thing. Okay, so that's going to be our two lines. This is what we already know, and this is what we're going to be working on. Now, just as in the case of 1D motion, we looked at two special cases. We looked at constant velocity motion and then constant acceleration motion. So we can have the same thing here. We could have constant angular velocity motion. So that's just some object is spinning at a constant rate. That happens a lot, right? So a record on a record player spins at a constant rate. Okay, so let's just talk about the formulas that would go along with it. There would be no acceleration, no angular acceleration, right? Because the velocity is not changing. The angular velocity would just be a number, right? A constant, that's the point, constant. And then your theta would be that number times t plus whatever initial position you started at. So these are kind of the same formulas, but now with these new variables for constant angular velocity motion. Let's do a quick example. A wheel rotates with a constant angular velocity of 11.5 radians per second. By how big of an angle does it rotate in 8 seconds? Okay, so we have a wheel. So I draw a circle. And it's rotating about its center, presumably. And I put a coordinate system on it. And because I get to choose, I'm going to do the smart thing and make my reference point. So at the beginning of this problem, my reference line is going to be at theta equals 0. So in other words, I'm saying theta, the initial theta is 0, because I'm just defining it that way. And this is akin to in regular 1D motion problems when we choose our coordinate system and we get to choose where the 0 is, and we unless there's a reason not to, we put 0 at wherever the object starts. Same thing, so I'm putting my reference line at the 0 angle, or I'm putting the 0 angle at the reference line, however you want to look at it. All right, so my theta formula for position will be, so 11.5 radians per second times time, and then it's just plus 0, so I don't even have to put that in. And now I want 8 seconds. So this is my formula, and I just plug in 8 seconds. And that'll tell me how many radians it has progressed. And I get 92.0 radians. Okay, so that's the answer to number 1. It will have gone around 92 radians. Now, 92 radians is a lot more than 2 pi radians, which is 1 full revolution. So if we wanted to, it's not asked for here, but if we wanted to, we could figure out a little bit more detail. How many times did it go around? Well, 2 pi, which is like, what, 6, pi is 3.14, so pi is like 6.28 radians. 2 pi is 6.28 radians. We could divide that in and see how many 2 pi's we have here. So 92 radians divided by 2 pi is something like 14.6-ish. So there would have been 14.6 revolutions. So in the 8 seconds, it would have gone around 14 times plus a little more than halfway around. So we can also do that kind of an analysis. All right, number 2, how long does it take for it to complete 1 full rotation? What's being asked for in that question is the period. Period is time for 1 rotation. It's measured in seconds, typically. So that's what we have to figure out. So 1 full rotation corresponds to a theta of 2 pi, right? Going around once is 2 pi. So I'm going to set theta equal to 2 pi in my formula here. So 2 pi equals 11.5 radians per second t. So I just divide, so I get t equals 2 pi divided by 11.5 radians per second. Technically, this 2 pi is in radians. I should be writing my units there as well. 2 pi radians. So radians divided by radians per second will give me seconds, which is right. And that gives me 0.546 seconds. So that would be the answer to question 2. And really, I should be using capital T here because it is the period. Okay. The second special case, almost as important, is constant acceleration, constant angular acceleration. So something is rotating, but it's either accelerating or maybe decelerating at a constant rate. Okay, so again, very analogous to one-dimensional motion. We're going to have, now, there is an acceleration, so that'll just be some number, whatever is given to us. The angular velocity then will be that number times t plus whatever the initial was. And then position is going to be that number divided by 2, t squared, plus initial velocity times t plus initial position. Remember, the initial position often will be 0 because we'll choose it to be that. But we can't choose the initial velocity to be 0. All right. Now, not only that, but maybe even more usefully, right, we have our 4 formulas from 1D motion, constant acceleration, that sort of compare an initial to a final. And we can have those as well here. So we can have 2 of them were just repeats of our equations of motion. So we could have like theta final equals so I'll put in alpha for that number sign that I was using. Alpha over 2 t squared plus omega I t plus theta I. So that, that's a formula that if you have alpha t, omega I, theta I, and theta f, you have that. You can, if you have 4 of those and are missing 1, you can use this formula to figure out the missing 1. You know how that works. The second one here also, I can say that omega f is alpha t plus omega I. And then the other two are going to be omega f squared equals omega I squared plus 2 alpha theta f minus theta I. This just comes from some algebra on these other ones. And then finally, theta f equals theta I plus 1/2 omega I plus omega f t. So there are our 4 convenience formulas for constant angular acceleration motion. All right, let's give it a shot. Let's give it a try, but we won't be using all 4 of these, but you just get a flavor for how these look. All right, a disk starts at rest and then begins to rotate with constant angular acceleration. After 5 seconds, it has rotated 25 radians. What is the angular acceleration? And then additional questions. Okay. So let's see. So for number 1, let's certainly choose our reference line to be at angle 0. And then our final is 25 radians. The time here is 5 seconds. We know it starts at rest, so omega I is 0. And we're looking for alpha. So looking at our formulas, I think, am I right that equation number 1 is going to give it to us? So we have theta f equals alpha over 2t squared plus omega I t plus theta I. We're looking for alpha, so I can bring the other guys over. Theta f minus theta I minus omega I t equals alpha over 2t squared. I can multiply by 2, divide by t squared. And that gives me alpha. Okay, and then I can just plug everything in, and I get, and I'm just going to pause and work this out real quick and then come back. And by the way, I should point out that this is 0 and this is 0, so they're not really even in the problem. And so, yeah, it ends up being 2, I believe. Hopefully I did that right. I guess I have 2 significant figures. So 2 radians per second squared is the acceleration. Okay. Number 2. What is the average angular velocity over the 5 seconds? Average angular velocity over the 5 seconds. Okay. So actually for that, I can just go back to this formula, which we have. It goes from 0 to 25 radians. So the change in theta was 25 radians. And it does that in 5 seconds. So 25 divided by 5 is 5 radians per second. That's its average speed. Of course, that's not its speed the whole time because it's accelerating. It starts at 0 radians per second. Okay. So 5 radians per second is the average. Number 3, what is the angular velocity at 5 seconds, at t equals 5 seconds? So what is its instantaneous velocity after the 5 seconds have elapsed? So looking back at my formulas, I'm looking for omega f. I'm looking for a final velocity after the 5 seconds. The first one is out because omega f isn't even involved. This one, though, is the simplest one that has omega f, and I have alpha because I just got it from number 1, and I have t, and I have omega I at 0. So that looks like the formula to use now. I could probably use the other ones as well, but they'd be slightly more complicated. So omega f equals alpha t plus omega I. It's already solved for omega f. I just plug in my numbers, 2.0 radians per second squared, answer from number 1, times 5 seconds, plus 0. So looks like 10 radians per second. That makes sense. It starts at 0, it ends at 10 radians per second, and its average was 5 radians per second. And that makes sense because it's accelerating steadily. And finally, number 4, by what angle had it rotated after 3 seconds? Okay, so again, we're choosing our reference line so that initial is 0. This is what we're looking for, the final position. We have our time. We do have acceleration. And we have initial velocity of 0. And yeah, so which equation gives us that? Is that the first one again? Yeah, I think so. We have all that. Okay. So theta f equals half of the acceleration t squared plus omega I t plus theta I. But yeah, this is 0 and this is 0, so it's just these three. So we have 2.0 radians per second squared over 2 times 3 seconds squared. That looks like 9 radians. 9 radians. All right. So that gives you a flavor for constant acceleration problems, very much like the corresponding one-dimensional motion problems that we did way back in Chapter 2. One last thing to talk about with the kinematics of rotational motion. We want to link these new angular quantities that we've been talking about with actual positions, like in meters. So let me explain. Let's assume the body is rigid. So let's say we have a disk spinning around. At any, in any given time period, as this thing spins, like let's say like a point here, after a little bit later, it moves to a point there. And a point a little bit further out moves to a point, whoops, right there. And maybe a point over here moves to a point there. Right? So different points on this object are rotating. I'm sorry, I didn't really make these very circular. They're supposed to be little circular paths. Yeah, in fact, that's the first thing I want to say is points are moving in a circle, right? They're going around in a circle. Like if you're a little speck of dust on this record, you're going around in a circle as the thing rotates. You're engaging in circular motion. But not every point moves the same distance, right? Points that are closer to the center of rotation, are not going to move as far as points way out on the edge. Points way out on the edge have to go further to go around. So we want to be able to tell how far a particular point goes. We're talking about angle, and all points move the same angle. But how many meters do they actually move? And here's the deal. Here's the actual formula. And actually, before I say the formula, the distance that it moves, we usually use the letter S for that. I'm not sure why. But how far you move, so I'll call that delta S, is you take the angle that you moved in and multiply by the radius. And this R is the radius. It's how far away you are from the center. Okay, so if you're on a record that's spinning and the record spins let's say 0.6 radians, 0.60 radians, but you're a little speck of dust that is 0.2 meters away from the center. So you're like right here. Okay, so this thing spins, and yeah, 0.60 radians is how much this thing has gone around. How far have you actually moved? This part right here, how long is that little path there? And the answer is, it's 0.2 meters times 0.60 radians, which is what? It's 0.12 meters. Yeah, let me give myself a second significant figure there. Okay, so 0.12 meters. By the way, right here, this formula is why we work in radians. If you didn't work in radians, you'd have to throw in a 2 pi somewhere. You'd either have to multiply or divide by 2 pi, so it would be a messier formula. But here it's just, okay, you want to turn theta angles into actual meters. You just multiply by how far away you are from the center. So that's good. Okay. Speeds are the same. So again, we have angular speed, angular velocity. That's telling you how many radians you're spinning per second. And if you multiply that by your radius from the center, that'll actually tell you how fast you're moving truly in meters per second. In meters per second. Okay, so that's a good formula as well. And then finally, acceleration. Now acceleration is a little bit special because remember there's two kinds of acceleration. There's the acceleration when you're going around in a circle, or anytime you're moving not in a straight line. The two kinds of acceleration. Tangential acceleration is the acceleration that is either speeding you up or slowing you down. And then centripetal acceleration is the acceleration that's turning you. So it turns out, so if you take your alpha, your angular acceleration, and multiply that by r, you get tangential acceleration. Tangential acceleration. Okay, so that's the corresponding formula. So again, we have position. Take delta theta, multiply r, you get delta s. Speed, take omega, and multiply by r, you get v. And acceleration, take alpha, multiply r, you get at, you get tangential acceleration. Now these points are moving in circles, so we know what the centripetal acceleration is. So if need be, we can figure that out, right? The v here can be gotten from over here. And then the overall acceleration is, you do a Pythagorean theorem on these two pieces of acceleration, tangential and centripetal. Okay. So a quick example of that. A disk starts at rest and then begins to rotate with constant angular acceleration. So this is actually like the previous example we did. But what's in bold here is some additional information. The radius of the disk is 0.75 meters. After 5 seconds, it has rotated 25 radians. That's just like before. So I want to know, what is the velocity and acceleration of a crumb at the edge of the disk after 5 seconds? So we have a little crumb right on the edge here that is 0.75 meters away. And it's, it's moving along. It's engaging in circular motion. All right, well, after 5 seconds. So I think we already figured out, what did we figure out from before? We figured out that was question 3. After 5 seconds, what was the angular velocity? And that was 10 radians per second. So we had omega was 10 radians per second. So v is just r times that. So 0.75 meters times 10.0 radians per second, 7.50 meters per second. Yeah, there you go. So that's how fast it's going in actual meters per second. That's its speed, that crumb's speed. it's going around at 10 radians per second. That's sort of like how much of an angle it's going through every second, but it's actually going through 7.5 meters every second. All right. Now for acceleration, yeah, we had figured out alpha. Alpha was 2.0 radians per second squared. And so now we're going to say that tangential acceleration is r times that. So 0.75 meters times 2 radians per second squared is going to be, what's that, 1.50 meters per second squared. Okay. Now that's just the tangential acceleration, though, not the full acceleration that I think we're being asked for. Centripetal acceleration is v squared over r, and we just figured out v, so 7.50 meters per second squared over 0.75 meters, which comes out to be 75.0 meters per second squared. So that's the acceleration that's responsible for the turning. So the full acceleration then is the square root of those two guys together, 1.50 meters per second squared plus 75.0 meters per second squared. And that comes out to be, well, okay, yeah, to three significant figures, it's actually still 75.0 meters per second squared. It's a little bit more, mathematically, it's a little bit more because of that 1.50 squared, but that's not going to add much when you do Pythagorean theorem. Okay, it just happened here that the centripetal acceleration was a lot bigger than the tangential acceleration, so almost all of the acceleration is centripetal, so it comes out to be the same thing. But that's how you do it. Okay, so that covers kinematics. And again, the take-home point is that it's very analogous to 1D motion. You just have to think in terms of angles now. But these last 5 to 10 minutes or so have been how we bridge back to actual meters and meters per second and meters per second squared. And that kind of covers everything.